More than 20 billion kilometers from Earth, Voyager 2 is the only functioning spacecraft in interstellar space. Since crossing the heliopause in 2018, it has been sending back measurements from a region no other active instrument has ever explored. What Voyager 2 detects is detected nowhere else. What it misses remains unknown. But the mission is running out of time. Launched in 1977, the spacecraft is powered by radioisotope generators fueled by plutonium-238. Each year, radioactive decay reduces its available electrical power, forcing instruments to shut down one by one. The end of the mission is not a destination, it is silence. Voyager 2's achievement is not simply distance. Distance alone is meaningless. What makes the spacecraft extraordinary is that it crossed billions of kilometers while remaining connected, continuing to transform an unexplored region of space into scientific knowledge. When that connection ends, the exploration ends with it. Voyager will keep traveling for billions of years, but it will do so as a silent artifact drifting through the galaxy. What Voyager 2 actually is, and why nothing like it exists. Voyager 2 is not a large spacecraft. It weighs approximately 825 kilograms, roughly comparable to a medium-sized grand piano, and its central structure is a decagonal bus roughly the size and shape of a large household appliance. Attached to this bus are a 3-meter high-gain antenna pointed continuously toward Earth, a magnetometer boom extending approximately 13 meters to keep the sensitive magnetic field instruments away from the spacecraft's own electromagnetic interference, a scan platform that once held cameras and spectrometers during the planetary encounter phase of the mission, and 3 radioisotope thermoelectric generators mounted on a separate boom to minimize their thermal and radioactive interference with the science instruments. This is the physical object that crossed the heliopause in 2018. This is the physical object that is currently sampling the interstellar medium. It is smaller than most living rooms, and it is more than 130 astronomical units from the Sun. The scientific instruments that remain operational on Voyager 2 are the product of 1970s technology, designed and built when the integrated circuits they depend on were fabricated using processes that would be considered primitive by contemporary standards. The onboard computers execute approximately 8,000 instructions per second. A modern smartphone handles more than 14 billion. The flight data system that formats data for transmission was designed to operate for 4 years during the primary planetary mission. It has now been running continuously for nearly 5 decades. The engineering margins built into the spacecraft were generous for their era, which is part of why the mission has lasted as long as it has. But no engineering margin was designed with interstellar space in mind. The Voyager program was conceived, funded and designed to study the outer planets. Everything after Neptune has been a bonus drawn from reserves that were never intended to sustain it. The instruments that were operating at the time of the heliopause crossing in 2018 included the Plasma Science Experiment, the Low Energy Charged Particle Instrument, the Cosmic Ray Subsystem, the Magnetometer, and the Plasma Wave Subsystem. 5 instruments, 5 distinct ways of measuring the environment outside the solar system. In October 2024, NASA shut down the Plasma Science Experiment, the instrument that had provided humanity's first direct measurement of interstellar plasma density, temperature, and flow. In March 2025, the Low Energy Charged Particle Instrument was shut down as part of a coordinated power conservation plan across both Voyager spacecraft. The Cosmic Ray Subsystem is scheduled for shutdown in 2026. After that, 2 instruments will remain: the magnetometer, measuring the direction and strength of the local interstellar magnetic field, and the plasma wave subsystem, detecting electromagnetic oscillations in the surrounding plasma from which the electron density can be inferred. These are not interchangeable measurements. Each instrument captures something distinct about the environment through which the spacecraft moves, and the loss of each one permanently closes a window that no other instrument on Earth or in space can replicate. The Plasma Science Experiment measured the plasma directly, the speed, density, temperature, and direction of the charged particles flowing through interstellar space. The magnetometer measures the magnetic field, which is related to but not the same as the plasma properties. The plasma wave subsystem infers density from the oscillation frequency of waves propagating through the plasma, a less direct measurement that provides complementary rather than redundant information. None of the measurements these instruments make can be obtained from telescopes on Earth or in Earth orbit. The interstellar medium at distances of 130 to 160 astronomical units can be probed from Earth only through remote sensing techniques that aggregate properties over enormous path lengths and cannot resolve the local conditions that Voyager 2 measures directly. There is no replacement mission in operation, in construction, or in funded development that will reach the interstellar medium within the careers of most people currently working in space science. NASA's proposed interstellar probe concept, developed under principal investigator Ralph McNutt at the Johns Hopkins Applied Physics Laboratory, envisions a mission that would travel to 1,000 astronomical units from the Sun, far beyond Voyager 2's current position, using a solar gravity assist maneuver and advanced propulsion. The concept has been studied in detail. It has not been funded. Even if it were funded tomorrow, the spacecraft would not reach the heliopause for several decades after launch. The gap between Voyager 2's end of mission and any future direct measurement of the interstellar medium is not measured in years. It is measured in decades at a minimum, and potentially in the lifetimes of people who are currently alive. Understanding that Voyager 2 is unique and irreplaceable in its current scientific role is the prerequisite for understanding why its final destination is worse than most accounts suggest. The spacecraft is not simply traveling to a place it will eventually reach. It is exhausting the last of the resources that allow it to tell us anything about the places it passes through. And it is doing so in a region where every measurement is historically unprecedented and where no successor will arrive for a generation. The power curve that cannot be reversed. The 3 radioisotope thermoelectric generators aboard Voyager 2 operate on a principle that is simple, elegant, and ruthlessly finite. Plutonium-238 is a radioactive isotope that decays by emitting alpha particles, releasing thermal energy as it does so. The thermoelectric generators convert this thermal energy into electricity using thermocouple junctions, solid-state devices that produce a voltage when one end is hotter than the other. There are no moving parts, no turbines, no combustion, no chemistry. The system is purely thermal and electrical, and it will continue to function as long as the temperature difference between the plutonium heat source and the cold outer space environment remains large enough to drive a measurable current through the thermocouple junctions. At launch in August 1977, the 3 generators together produced approximately 470 watts of electrical power. This was never a large budget. A typical household microwave oven consumes around 1,000 watts. 4 or 5 incandescent light bulbs would have exhausted the entire power supply of Voyager 2 at launch. Every instrument, every computer, every heater, every thruster controller, every transmitter circuit, and every bit of data processing required to run an active interplanetary and eventually interstellar mission was powered by those 470 watts. Plutonium-238 has a half-life of approximately 87.7 years, meaning that every 87.7 years, half of the remaining plutonium atoms have decayed into daughter products and are no longer contributing to the thermal output. The decline is not sudden. It proceeds continuously, which in practical terms means the spacecraft loses approximately 4 watts of electrical output every year. At the time Voyager 2 reached Jupiter in 1979, the generators were producing roughly 460 watts. By the Neptune flyby in 1989, the output had dropped to approximately 400 watts. By 2010, it was around 270 watts. By 2020, approximately 235 watts. In 2026, The usable output is estimated at somewhere in the range of 210 to 220 watts, depending on thermocouple degradation and system efficiencies that have themselves changed over nearly 5 decades of operation. The 4-watt annual decline sounds small in isolation. It is devastating in context. At 210 watts of total output, after accounting for electrical losses and conversion inefficiencies, the spacecraft has a working power budget that must simultaneously cover the attitude control system, the onboard computers, the heaters that prevent the hydrazine thruster fuel from freezing solid in the cold of deep space, and any scientific instrument still operating. Each of these systems has a minimum power threshold below which it simply stops functioning. The attitude control system must maintain the high-gain antenna pointing to within a fraction of a degree of Earth to sustain the communication link. If the antenna drifts off target, the signal is lost and commands cannot be received. If commands cannot be received, nothing else can be corrected remotely. The computers must process incoming commands and format outgoing data. The transmitter must push its signal across more than 130 astronomical units of vacuum at a power level that, by the time the signal reaches Earth, delivers less than 1/10 of a quadrillionth of a watt to the receiving antenna. The heaters deserve specific attention because they represent the most acute tension in the power budget. Hydrazine, the monopropellant fuel used by Voyager 2's attitude control thrusters, freezes at approximately 2 degrees Celsius. The environment through which the spacecraft travels has an ambient temperature of approximately 2.7 Kelvin, barely above absolute zero. Without continuous electrical heating, the fuel lines and thruster valves would freeze within days. Frozen fuel means non-functional thrusters. Non-functional thrusters mean the spacecraft cannot maintain its attitude, cannot keep the antenna pointed at Earth, and cannot receive new commands or transmit useful data. The entire mission collapses not from a dramatic component failure, but from the simple thermodynamics of an unheated fuel line in the cold of space. Mission engineers at the Jet Propulsion Laboratory have been making difficult decisions about heater power for years. Each time a heater is turned off, a few watts are freed for other uses, but the risk of fuel line freezing increases. Several heaters have already been shut down, accepting elevated risk in exchange for extending the operational life of scientific instruments. These are not easy decisions, they are irreversible. A heater that is turned off cannot be turned back on without consuming the same power that was saved by shutting it down, and the power budget has no margin for recovery from errors. Every decision to shut down a heater is a permanent increase in the probability that the mission ends not in a planned gradual shutdown, but in an uncontrolled loss of attitude control. The degradation of the thermocouple junctions themselves adds a further complication that the simple 4-watt per year figure does not fully capture. Thermocouple efficiency declines over time as the metallic alloys in the junctions undergo subtle atomic level changes under the combined effects of radiation, thermal cycling, and age. The rate of this degradation was measured carefully during the mission's early years and incorporated into power models, but the models were built from data spanning the first decade or two of operation. Extrapolating them to nearly 5 decades introduces genuine uncertainty. The actual power output in any given year may be slightly more or less than the model predicts, and in a budget this tight, the difference matters. The power curve cannot be reversed. No technology exists or is under development that could refuel a radioisotope thermoelectric generator from a distance of 130 astronomical units, or from any distance. The plutonium-238 that remains in the generators is decaying according to the laws of nuclear physics, which are not subject to engineering workarounds. The mission team at JPL can manage the decline, choosing which systems to sacrifice and which to preserve, but they cannot stop it. The curve runs in one direction and the direction is down, 4 watts per year every year, until the transmitter falls below the minimum power threshold needed to push a signal across the expanding distance to Earth. the heliopause crossing and what was found there. When Voyager 2 crossed the heliopause in November 2018, the event was not announced as a surprise. Scientists had been watching the spacecraft's instruments for signs of the boundary for years, building on Voyager 1's crossing in August 2012 and refining their predictions about what Voyager 2 would find when it reached the same boundary in a different region of the sky. But what the instruments actually measured at the crossing differed from the predictions in ways that forced significant revisions to models of the heliosphere's structure, and those revisions are still being worked through. The heliopause is the surface where the outward pressure of the solar wind, the continuous stream of charged particles flowing from the Sun in all directions, exactly balances the inward pressure of the interstellar medium, the diffuse gas, dust, and plasma that fills the space between stars. Inside the heliopause, the environment is dominated by solar wind particles and the Sun's magnetic field. Outside it, the environment is dominated by the local interstellar medium. The transition is not a physical barrier. It has no material existence. It is a pressure boundary, a dynamic equilibrium between two flows, and it moves inward and outward in response to changes in solar activity over the 11-year solar cycle. The crossing itself was sharp by the standards of what models had predicted. Some theoretical frameworks suggested the boundary would be a broad, gradual transition zone spanning tens of astronomical units. Instead, Voyager 2's instruments recorded a transition that occurred over at a distance of roughly 1 astronomical unit, approximately the distance from Earth to the Sun. Within that distance, the solar wind speed dropped precipitously. The plasma science experiment recorded the transition directly. The flow of solar wind particles that had been a constant companion of the spacecraft for 41 years essentially ceased. The interstellar plasma, flowing in from outside, replaced it. The magnetic field shifted direction. The cosmic ray flux, which had been increasing as the spacecraft approached the heliopause from inside, made a sharp upward jump as the shielding effect of the heliosphere was left behind. The temperature of the plasma at the crossing was among the most unexpected findings. The heliosheath, the turbulent region just inside the heliopause where the slowed solar wind piles up before the boundary, was expected to contain plasma at elevated temperatures due to the compression and thermalization of the decelerated solar wind. Both Voyager 1 and Voyager 2 found plasma temperatures in the heliosheath that were lower than some models predicted, but higher than others. The immediate post-crossing region inside the interstellar medium just beyond the heliopause showed plasma properties that differed between the two spacecraft's crossing locations. This asymmetry confirmed what models had suggested. The heliosphere is not a symmetric sphere. It is shaped by the Sun's motion through the interstellar medium, which compresses the boundary in the direction of travel and extends it in the trailing direction, and the properties of the boundary and the medium just beyond it vary with position around the heliosphere. The crossing confirmed something else that had been debated. The heliopause is a relatively sharp, well-defined boundary. Theories had proposed various mechanisms that might blur or broaden the transition, including magnetic reconnection between the heliospheric and interstellar magnetic fields, and the diffusion of energetic neutral atoms across the boundary. The measurements from both Voyager crossings supported a relatively clean transition, suggesting that these broadening mechanisms were less effective than some models proposed. But the detailed structure of the boundary, its precise thickness, the nature of the turbulence at and just beyond it, the specific mechanisms controlling particle transport across it, remain areas of active research because the only data available come from 2 points separated in space and time, each sampled during a single pass by a single instrument suite. Perhaps the most significant finding from the heliopause crossing was the direct measurement of the interstellar plasma density on the other side. Voyager 1's plasma science experiment had failed decades before its crossing, so that spacecraft could not directly measure the plasma properties in the interstellar medium. Voyager 2's plasma science experiment was still functioning in 2018. making it the first instrument to directly measure the density, temperature, and flow of the plasma beyond the heliopause. The electron density in the local interstellar medium measured by the plasma science experiment was approximately 0.12 electrons per cubic centimetre, higher than most pre-crossing model predictions. This higher density means the interstellar medium is pressing more firmly against the heliosphere than expected, which has implications for the heliosphere's size, shape, and shielding effectiveness. The measurement existed for approximately 6 years before the plasma science experiment was shut down in October 2024. 6 years of direct interstellar plasma measurements, unique in the history of science, now closed. The plasma wave subsystem can infer electron density from oscillation frequencies in the plasma, providing a less direct but still valuable proxy measurement. But the direct measurement, the actual sampling of the interstellar plasma flow, is gone. The scientific community is currently working with 6 years of data from a single instrument at a single location. That is what exists. That is what there is. The instruments that are gone and what was lost with them. To understand the significance of each instrument shutdown, it helps to be specific about what each one measured and why that measurement cannot be replicated by any other means currently available. The shutdowns are not the removal of redundant capability. Each instrument that goes dark eliminates a unique scientific capacity that existed at exactly one place in the universe, aboard Voyager 2. The plasma science experiment, shut down in October 2024, contained 4 sensors that measured different properties of the charged particle population surrounding the spacecraft. A Faraday cup sensor measured the bulk flow of plasma, determining the speed, density, and direction of the solar wind inside the heliosphere and the interstellar plasma outside it. Electrostatic analyzers measured the energy and direction of individual ions and electrons. Together, these sensors provided a direct characterization of the plasma environment that is unattainable by any remote sensing technique. The density and temperature of plasma can be inferred from remote observations, but the inferences carry large uncertainties and reflect conditions averaged over vast distances. A point measurement at a specific location gives numbers that remote sensing cannot match in precision. The instrument was shut down not because it had failed, but because its orientation relative to the interstellar plasma flow direction had made its measurements increasingly difficult to interpret in the years following the heliopause crossing. The solar wind flows outward in all directions from the Sun, so the plasma science experiment was designed for a geometry where the flow comes from ahead of the spacecraft as it moves away from the Sun. The interstellar plasma does not flow from behind the spacecraft in the same geometrically clean way. The instrument was collecting data, but the data required complex corrections for flow direction that reduced its scientific value. The power it consumed could be redirected to other instruments with better geometric alignment to the interstellar environment. The decision was scientifically defensible. The loss was nonetheless real and permanent. The low-energy charged particle instrument, shut down in March 2025, measured ions and electrons with energies ranging from a few thousand to a few million electron volts. This energy range is particularly relevant for studying 2 populations: the energetic neutral atoms and ions produced in the heliosheath as solar wind particles undergo charge exchange with interstellar neutrals, and the anomalous cosmic rays that are accelerated at the termination shock, the inner boundary of the heliosheath, where the solar wind abruptly decelerates. The instrument also measured galactic cosmic rays at the lower end of their energy spectrum, providing complementary data to the cosmic ray subsystem, which measures the higher energy cosmic ray population. The loss of the low-energy charged particle instrument removes Voyager 2's ability to directly measure the lower energy component of the cosmic ray spectrum in the interstellar medium. Galactic cosmic rays are a subject of considerable scientific interest because they are produced by energetic astrophysical processes, primarily supernova remnants, throughout the galaxy, and their propagation through interstellar space depends on the magnetic field structure density, and turbulence of the medium through which they travel. Measuring the cosmic ray spectrum directly in the local interstellar medium, rather than inferring it from the spectrum measured inside the heliosphere with corrections for heliospheric modulation, provides a ground truth that has never been available before Voyager's measurements and will not be available again after them. The cosmic ray subsystem, scheduled for shutdown in 2026, measures the highest energy cosmic rays and also detects electrons and some heavier nuclei. Its contribution is complementary to the low-energy charged particle instrument at the high end of the energy spectrum. Together, the two instruments would have provided a reasonably complete picture of the charged particle energy spectrum in the local interstellar medium across 5 orders of magnitude in energy. With the low-energy instrument already gone and the cosmic ray subsystem scheduled to follow, the charged particle measurements from Voyager 2 will cease entirely. The magnetometer and plasma wave subsystem can still tell us about the field and plasma properties of the interstellar medium, but they cannot replace the direct particle measurements. Each of these losses is compounded by the absence of any follow-on measurement. When a temperature sensor fails on a weather station, other stations continue to operate, and satellites provide complementary data. The loss is real, but not catastrophic for the measurement program as a whole. When a Voyager instrument shuts down, there is no other station. The space between the stars at 130 to 160 astronomical units from the Sun is occupied by exactly one active human-made scientific instrument platform, and that platform is losing its instruments one by one on a schedule that cannot be altered. The 2023 near loss and what it revealed about fragility. On July 21, 2023, mission controllers at the Jet Propulsion Laboratory sent a routine sequence of commands to Voyager 2. Among the instructions was one that inadvertently rotated the spacecraft's antenna 2 degrees away from its pointing toward Earth. 2 degrees is a barely perceptible angle by everyday standards. Held at arm's length, a thumb covers approximately 2 degrees of sky. In the context of an antenna designed to communicate across more than 20 billion kilometers, 2 degrees is the difference between connection and silence. The high-gain antenna on Voyager 2 has a beam width of approximately 0.5 degrees at the transmission frequencies the spacecraft uses. When the antenna is pointed correctly at Earth, the transmitted signal arrives at Earth's receiving antennas with enough power to be detected and decoded, even after the inverse square law attenuation across 130 plus astronomical units reduces it to a tiny fraction of a watt. When the antenna is 2 degrees off target, the main beam entirely misses Earth. The received signal drops to 0, not to a low value, not to a degraded but partially recoverable level, to 0. From Earth's perspective, the spacecraft disappears. The communication link went dark. Mission controllers monitoring the telemetry feed observed the signal vanish during a tracking pass and immediately began the process of diagnosing the problem. They knew relatively quickly that the most likely cause was an attitude anomaly rather than a catastrophic spacecraft failure, because the pattern of signal loss was consistent with an off-pointing antenna rather than with a transmitter failure or a power loss. But knowing the probable cause and being able to fix it were entirely separate challenges. Voyager 2 is designed with fault protection software intended to handle exactly this kind of anomaly. If the spacecraft loses communication with Earth for an extended period, the fault protection system is programmed to sweep the antenna through a systematic search pattern until the Earth signal is reacquired. This is the autonomous recovery capability that the Voyager program's designers built in decades ago, anticipating that a spacecraft operating at interstellar distances cannot rely on timely human intervention to correct every problem. A command sent from JPL takes approximately 19.5 hours to reach Voyager 2 at this distance. A response takes another 19.5 hours to return. Every diagnostic and correction cycle is a 39-hour round trip at minimum. For 2 weeks, mission controllers attempted to restore the link. They used the Deep Space Station 43 dish in Canberra, Australia, the largest transmitting antenna in the Deep Space Network at 70 metres in diameter, to broadcast commands at maximum power in the general direction of Voyager 2. The commands were not aimed precisely along the antenna's main beam path, because the main beam was not pointing at Earth. Instead, the signals were broadcast in a pattern intended to reach the spacecraft through its side lobes, the weaker peripheral reception zones outside the main beam, hoping to trigger the fault protection routine. The power delivered to Voyager 2 through the side lobes is far less than through the main beam, and triggering a fault protection response required sufficient signal strength to exceed the receiver's detection threshold through a secondary reception path. On August 4, 2023, 14 days after the signal was lost, the Deep Space Network detected a carrier signal from Voyager 2. The fault protection system had activated. The antenna had swept through its programmed search pattern, found Earth, and locked on. Commands could flow again. The link was restored. Normal operations resumed. The incident exposed something that the mission's operational history had obscured: how close to the edge Voyager 2 actually operates. 2 degrees of pointing error produced by a routine command sequence was sufficient to sever communication for 2 weeks. The recovery depended on the correct function of fault protection software written decades ago, and not updated since, on the continued availability of the most powerful transmitting antenna in the Deep Space Network, and on the fortunate geometry that placed the spacecraft in a position where the fault protection sweep pattern would eventually intersect Earth's location. Any of these factors could have been different. The software could have failed to trigger. The antenna could have been unavailable for other missions. The geometry could have been less favourable. The 2023 incident also revealed a structural vulnerability in Voyager 2's continuing operations that has become more significant since. The Deep Space Station 43 dish in Canberra is the only antenna in the Deep Space Network with enough transmitting power to send commands to either Voyager spacecraft. The Goldstone dishes in California and the Madrid antennas in Spain can receive signals from the Voyagers but cannot transmit commands to them. In May 2025, Deep Space Station 43 went offline for scheduled upgrades expected to last until February 2026. For approximately 9 months, with only brief windows of availability in August and December, Voyager 2 operated without the ability to receive new commands from Earth. Mission controllers had to anticipate every possible operational scenario, preload contingency command sequences, and essentially program the spacecraft to manage itself for months without human intervention. If anything went wrong during that period that the preloaded contingencies did not cover, the team could hear about it, but could not respond until the antenna came back online. The Canberra antenna maintenance window illustrates a systemic fragility in the Voyager program's end-of-mission phase. The entire 2 spacecraft mission depends on a single 70-metre antenna in Australia for uplink capability. That antenna requires maintenance. The maintenance windows are not negotiable for a facility serving the entire Deep Space Network. The mission must plan around them, accepting extended periods of one-way communication in which the science data continues to flow down, but no commands can flow up. In the mission's earlier years, when the spacecraft systems were healthier and the power margins were larger, this was a manageable constraint. In the current phase, where power margins are thin and any anomaly could require rapid command intervention, it is a source of genuine concern. What the interstellar medium actually is and why measuring it matters. The interstellar medium is not empty space. It is a diffuse mixture of gas, dust, charged particles, magnetic fields, and electromagnetic radiation that occupies the volume between stellar systems throughout the galaxy. Its properties determine how stars form from collapsing gas clouds, how supernova remnants expand and cool over millions of years, how cosmic rays propagate across galactic distances, and how the radiation environment experienced by any planetary system changes as the solar system orbits the galactic center over hundreds of millions of years. Understanding the interstellar medium is not an abstract scientific exercise. It connects directly to understanding the long-term history of the conditions under which life on Earth developed. The interstellar medium is not uniform. It is structured across an enormous range of scales, from the densest molecular cloud cores, where hydrogen densities reach 1 million molecules per cubic centimetre, to the hot ionized medium that fills much of the volume of the galaxy at temperatures of millions of Kelvin, but densities of only a few thousandths of a particle per cubic centimetre. The local interstellar medium, the region immediately surrounding the solar system within a few hundred light years, has a specific character that has been studied through remote observations of stellar absorption spectra, pulsar dispersion measurements, and the scattering of ultraviolet light from hot stars. These observations suggest that the solar system is currently embedded in a region called the local bubble, a cavity of hot, low-density gas approximately 300 light-years across, that was excavated by a series of supernova explosions roughly 10 to 20 million years ago. Within the local bubble, the solar system resides in a denser structure called the local interstellar cloud, a warm, partially ionized cloud with a density of approximately 0.2 to 0.3 atoms per cubic centimetre and a temperature of roughly 6,000 Kelvin. The heliosphere is embedded in this cloud, and the properties of the local interstellar cloud determine the properties of the interstellar medium that Voyager 2 is now measuring directly. The electron density measured by the plasma wave subsystem after the heliopause crossing, approximately 0.12 electrons per cubic centimetre, is consistent with the local interstellar cloud environment inferred from remote sensing, though the direct measurement is more precise and more localised than anything achievable from Earth. Why does measuring the local interstellar medium directly matter, beyond the intrinsic scientific value of knowing the properties of the environment surrounding the solar system? The answer connects to the heliosphere's role as a protective bubble. The heliosphere deflects and modulates a significant fraction of galactic cosmic rays before they can reach the inner solar system. The degree of modulation depends on the properties of both the heliosphere and the interstellar medium pressing against it from outside. A denser interstellar medium compresses the heliosphere to a smaller size, reducing its shielding effectiveness. A stronger interstellar magnetic field alters the heliosphere's shape and the pathways by which cosmic rays can penetrate it. Changes in the local interstellar environment, which occur as the solar system orbits the galactic center over periods of tens to hundreds of millions of years, alter the cosmic ray flux reaching Earth's surface. Cosmic rays have biological consequences. High-energy charged particles penetrating the atmosphere produce secondary particles at ground level, contributing to the natural background radiation that living organisms have evolved to tolerate, and that at elevated levels can cause DNA damage, mutations, and increased cancer rates. The cosmic ray flux reaching Earth's surface is not constant across geological time. It varies as the heliosphere's size and shielding effectiveness change in response to changes in solar activity on timescales of years, changes in the local interstellar medium on timescales of millions of years, and passages through denser interstellar structures such as molecular cloud arms on timescales of tens of millions of years. Some researchers have proposed connections between periods of elevated cosmic ray flux and periods of elevated mutation rates in the geological record, though these connections remain speculative. Voyager 2's measurements of the actual properties of the local interstellar medium, including the plasma density, the magnetic field strength and direction, and the plasma wave spectrum, provide the ground truth against which models of heliospheric shielding and cosmic ray modulation can be calibrated. These are not measurements that remote sensing can provide with comparable precision. The electron density measured directly by the plasma wave subsystem constrains the heliospheric models in ways that pulsar dispersion measurements, which average over paths of hundreds to thousands of light years, cannot. The magnetic field measured by the magnetometer directly in the local interstellar medium constrains the field's strength and direction in a volume immediately surrounding the solar system that is inaccessible to any Earth-based observation. When Voyager 2's instruments go dark, this calibration data stops accumulating. The models that have been refined using Voyager measurements will continue to be used, but they will no longer be updated with new direct observations. The properties of the interstellar medium at the distances Voyager 2 will travel after its instruments die will remain inferred rather than measured, returning to the pre-Voyager situation in which everything about the local interstellar environment was known only through the filtered and average signals of remote sensing. The pristine interstellar medium, and whether Voyager 2 will reach it. One of the most consequential open questions in heliospheric physics is whether Voyager 2's remaining instruments will survive long enough to sample what researchers call the pristine interstellar medium, the undisturbed environment that exists beyond the region perturbed by the heliosphere's interaction with its surroundings. The heliosphere does not sit passively in the interstellar medium like a bubble in still water. It moves through the interstellar medium at roughly 23 kilometers per second relative to the local standard of rest, which is the average velocity of stars in the Sun's galactic neighborhood. This motion creates a bow wave, or more precisely, a bow shock, or a bow wave depending on whether the relative velocity is supersonic or subsonic in the interstellar medium that compresses the interstellar material ahead of the heliosphere in the direction of the Sun's motion. Behind the heliosphere, in the trailing direction, the solar wind exhausted after crossing the heliopause creates a heliotail, a region of modified solar material extending downwind like the wake of a ship. The region immediately surrounding the heliosphere in all directions is therefore not pristine interstellar medium. It is a disturbed zone where the heliosphere's presence has altered the density, temperature, magnetic field, and flow properties of the gas and plasma. Pressure waves generated by solar activity, including coronal mass ejections and solar flares, propagate outward through the heliosphere, cross the heliopause, and continue into the interstellar medium for some distance before their energy dissipates into the surrounding plasma. The heliosphere's magnetic field connects to the interstellar magnetic field at the heliopause through complex processes including reconnection, and the resulting field geometry in the region just outside the heliopause reflects this interaction rather than the unperturbed interstellar field. Voyager 2 crossed the heliopause at approximately 119 astronomical units and is now at approximately 143 astronomical units. The distance at which the disturbance from the heliosphere's presence becomes negligible, at which the medium transitions from disturbed to pristine, is not precisely known because it has never been measured. Theoretical models suggest the disturbed zone might extend anywhere from a few tens to perhaps 100 astronomical units beyond the heliopause, depending on the properties of the local interstellar medium, the solar activity level, and the specific direction in which one measures. In the direction Voyager 2 is travelling, the current best estimates suggest the spacecraft may be approaching the transition between disturbed and pristine medium, but cannot confirm it because the instruments needed to definitively identify pristine conditions are being shut down. The plasma science experiment, which directly measured plasma flow properties, would have been the most useful instrument for detecting the transition to pristine interstellar medium because pristine medium would show a uniform undisturbed plasma flow uncontaminated by solar material. That instrument was shut down in October 2024. The low-energy charged particle instrument, which could have detected the absence of energetic particles of solar origin, was shut down in March 2025. The cosmic ray subsystem, whose measurements would show a change in the spectrum of cosmic rays reaching the spacecraft if the heliospheric modulation became negligible, is scheduled for shutdown in 2026. The instruments that remain, the magnetometer and the plasma wave subsystem can provide partial evidence about whether the spacecraft has reached the pristine interstellar medium. The magnetic field should show a transition to a more uniform direction and magnitude consistent with the background galactic magnetic field in the local interstellar medium. The plasma wave subsystem should show a change in the wave spectrum and possibly the electron density as the influence of heliospheric perturbations decreases. But these measurements provide less definitive evidence of the transition than the instruments that are already gone or scheduled to shut down. The scientific question of whether Voyager 2 will measure the pristine interstellar medium before its instruments die is therefore largely already answered by the sequence of shutdowns. The instruments best suited to make that determination are gone. The instruments that remain can provide evidence, but not proof. The spacecraft may move through the transition into pristine interstellar medium while still operating its last two instruments, and those instruments may detect the change. Or the instruments may shut down before the transition is reached. Or the transition may be so gradual that it is not clearly identifiable in the data from the remaining instruments. All three outcomes are scientifically meaningful, and only one of them, the first, provides the historically unprecedented measurement of undisturbed local interstellar medium that researchers have been hoping Voyager 2 might achieve. The probability that Voyager 2 will achieve this measurement depends on how far beyond the heliopause the disturbed zone extends in the direction the spacecraft is travelling, and how long the magnetometer and plasma wave subsystem continue to operate before their power requirements exceed what the declining RTG output can supply. Both quantities carry significant uncertainties. The mission is a race between the spacecraft's declining power and the distance to a measurement that, if achieved, would provide a scientific return worth every decade of the mission's extended life. The golden record as a relic, not a message. The golden record attached to Voyager 2's exterior is one of the most philosophically evocative objects humanity has ever sent into space, and it is worth examining honestly in terms of what it is and what it can realistically accomplish, rather than in terms of the romantic narrative that surrounds it. The record was designed and assembled in 1977 under the direction of Carl Sagan at Cornell University, working with a committee that included Anne Druyan, Frank Drake, Timothy Ferris, John Lomberg and Linda Saltzman-Sagan. It is a 12-inch gold-plated copper disc, its playing surface protected by an aluminum cover electroplated with a thin layer of ultra-pure uranium-238. The uranium serves a precise scientific purpose. It decays with a half-life of approximately 4.5 billion years, and a sufficiently sophisticated finder could use the ratio of remaining uranium to its decay products to calculate how long ago the record was made. It is a clock built from nuclear physics, designed to remain readable for timescales vastly exceeding human civilization's current duration. On the record are encoded 115 images, including photographs of Earth's geography, human anatomy, mathematical and physical concepts, and the diversity of terrestrial life. There are greetings from then United States President Jimmy Carter, from United Nations Secretary-General Kurt Waldheim, and from children representing various countries. There are spoken greetings in 55 human languages. There are sounds of earth, ocean waves, wind, thunder, the calls of birds and whales, the sound of a mother speaking to her infant, a human heartbeat, and a variety of other natural and human-generated sounds. There are 90 minutes of music drawn from traditions across human history and geography, including compositions by Bach, Beethoven, Mozart, Louis Armstrong, Chuck Berry, and Blind Willie Johnson. The probability that this record will ever be found by any intelligence capable of reading it is, in the honest assessment of the scientists who designed it, extremely small. Small is arguably an understatement. Human intuition is calibrated for terrestrial scales. We understand what it means to lose an object because every environment we evolved in is crowded with other objects. A ring can be lost in a house. A ship can be lost in an ocean. Even the most remote places on Earth exist within a world dense with matter, activity, and opportunities for discovery. Interstellar space is different. It is not merely large, it is almost entirely empty. The Milky Way contains hundreds of billions of stars, but those stars occupy only a tiny fraction of its volume. The overwhelming majority of the galaxy consists of darkness and distance. If every star in the Milky Way were reduced to the size of a grain of sand and spread proportionally across the continental United States, the average separation between grains would still be measured in kilometers. Voyager 2 is not one of those grains. It is a microscopic fragment moving between them. The challenge is not simply that another civilization would need to find it. The challenge is that they would first need to know there was something worth finding. Astronomy works because the objects astronomers study announce their existence. Stars produce enormous quantities of light. Pulsars emit regular radio signals. Quasars outshine entire galaxies. Even planets can be detected because they influence the stars they orbit. Voyager 2 does none of these things. Once its transmitter falls silent, it will emit no meaningful signal into the galaxy. It will become a cold piece of metal moving through darkness, reflecting only a tiny amount of starlight and generating almost no detectable signature of any kind. The distinction matters because the golden record is often described as a message. In a literal sense, it is. In a practical sense, it is not. Communication requires more than information. It requires transmission, reception, and interpretation. The golden record possesses information in extraordinary abundance, but it lacks any mechanism ensuring reception. It is less like a radio broadcast and more like a sealed archive placed in a location that no map identifies and no traveller is expected to visit. There is also the question of time. Human civilization often treats longevity as a solution to probability. If something exists long enough, eventually someone will encounter it. The universe does not necessarily work that way. Voyager 2 may survive for hundreds of millions or even billions of years, but survival alone does not increase visibility. A book drifting through the ocean does not become easier to find merely because it remains afloat for a longer period. The same principle applies in interstellar space. The spacecraft's future lifespan is measured in geological and astronomical timescales, but the volume through which it travels is so immense that those timescales may be irrelevant. This creates a strange contrast between the durability of the record and the fragility of the civilization that created it. The sounds encoded on the disk may outlast every nation currently on Earth. They may outlast every city, every language, every monument, every institution, and every cultural tradition that now exists. Long after the continents have shifted and the sun has grown brighter and transformed the surface of Earth, the grooves on the record may still contain the sound of a human heartbeat and the music of Bach and Chuck Berry. The artifact may survive while its creators become a distant and irrecoverable memory. That possibility reveals the golden record's real significance. Its value does not depend on discovery. It does not depend on extraterrestrial listeners or future contact. The record is important because it documents a moment when a technological civilization looked out at a universe it knew to be unimaginably vast, understood that the probability of being heard was close to zero, and chose to speak anyway. The gesture was never primarily about the recipient, it was about the sender. Choosing what to include required humanity to answer a question that civilizations rarely ask directly. If this were our only introduction, what would we say? The resulting record is therefore less a message to aliens than a portrait of humanity in 1977. It captures what a small group of scientists, artists, musicians, and thinkers believed was worth preserving about an entire species. Whether anyone ever listens is almost beside the point. The existence of the record tells us something important about the people who created it. Faced with silence on a galactic scale, they responded with a greeting. Space is empty in ways that human intuition cannot fully accommodate. Voyager 2 is a spacecraft roughly the size of a car, travelling through a galaxy that is 100,000 light-years across and contains 200 to 400 billion stars. The volume of space the galaxy occupies is so large that the spacecraft could travel for the remaining age of the Sun without coming within light-years of another stellar system, unless its trajectory happened to direct it towards one. Voyager 2 will make its closest approach to another star system, passing approximately 1.7 light-years from the red dwarf Ross 248 in roughly 40,000 years. That is a close pass by astronomical standards and an impossibly remote encounter by any practical standard. Even if an intelligence existed around Ross 248 or any other star that Voyager 2 passes near in the deep future, detecting a spacecraft the size of a car at a distance of 1.7 light-years would require observational technology so far beyond anything humanity possesses that comparison is not meaningful. And by the time Voyager 2 makes any of its future stellar approaches, its instruments will have been dead for tens of thousands of years, its transmitter silent, its fuel exhausted, its attitude control systems long since failed. It will be a passive, dark object with no electromagnetic signature distinguishing it from any other piece of cold metal drifting through the interstellar medium. Carl Sagan understood this. He was not naive about the probabilities involved. He believed the golden record was worth making, not primarily because it would be found, but because making it was an act of self-definition for the species doing the making. Choosing what to include on the record required answering questions that humanity rarely asks itself explicitly. Who are we? What do we value? What would we want a stranger to know about us? The answers encoded on the record reveal something about human civilization at a specific moment in its history that the record itself will preserve long after every artifact of that civilization has been destroyed by time, geology, stellar evolution, or other processes. But it is worth being clear about what the golden record is not. It is not a functioning communication system. It is not likely to ever be received. It is not a message in any practical sense. It is a relic, a physical artifact of a civilization that built a spacecraft and sent it as far as the laws of physics allowed. The romantic narrative of the golden record travelling forever, carrying humanity's music and voices through the galaxy for billions of years, is true as a description of the physical object's fate. It is misleading as an account of the object's communicative function. The record will travel. It will carry its encoded information intact for geological timescales. No one will hear it. The significance of the golden record, honestly assessed, is about what it says concerning the species that made it. That at the moment of sending a spacecraft into the interstellar void, humans felt compelled to include a greeting. That impulse, the need to reach out even when no response is expected, even when the probability of contact approaches zero, says something genuine about human nature. But that significance belongs to 1977, to the committee that assembled the record, to the culture that decided a spacecraft departing the solar system should carry something more than scientific instruments. The record's future is silence and drift, and the silence is the dominant fact. The Deep Space Network and the infrastructure of farewell. The Deep Space Network is the global antenna system that makes communication with Voyager 2 possible. Without it, the mission ends immediately and completely, regardless of how much power the spacecraft retains. The network consists of 3 complexes located approximately 120 degrees of longitude apart to provide continuous coverage of the sky. The Goldstone Deep Space Communications Complex in the Mojave Desert of California, the Madrid Deep Space Communications Complex near Robledo de Chavela in Spain, and the Canberra Deep Space Communications Complex near Tidbinbilla in Australia. Each complex contains multiple antenna dishes of different sizes, with the largest dishes at 70 metres in diameter. The 70-metre dishes are the critical element for Voyager communications. At Voyager 2's distance, the signal received on Earth has been attenuated by the inverse square law over more than 130 astronomical units of travel, until it carries a power at the receiving antenna of approximately 10 to the minus 16 watts, less than 1/10 quadrillionth of a watt. Detecting this signal requires antennas as large as physically buildable, cooled amplifiers operating at temperatures near absolute zero to minimize their thermal noise contribution, sophisticated digital signal processing to extract the coherent signal from the background noise, and very long integration times to accumulate enough signal energy for reliable decoding. Even with all of these capabilities, the data rate that Voyager 2 can support has declined dramatically from its planetary encounter days, where the spacecraft once transmitted at tens of thousands of bits per second. It now communicates at approximately 160 bits per second, roughly comparable to the telegraph technology of the 19th century. The single 70-metre transmitting antenna at Canberra, Deep Space Station 43, is the only facility capable of sending commands to either Voyager spacecraft. The Goldstone and Madrid antennas have transmitters, but they are not powerful enough to push a signal through the inverse square law attenuation across Voyager 2's distance. This creates a structural dependency that the mission cannot work around. If Deep Space Station 43 is unavailable, commands cannot be sent. The spacecraft can continue to transmit, and receiving stations at all three complexes can continue to collect the science and engineering data it sends down. But nothing can be changed, corrected, commanded, or updated from the Earth side. The 2025 to 2026 maintenance period for Deep Space Station 43 placed the mission in exactly this situation for approximately 9 months. Mission controllers had to prepare the spacecraft for extended autonomous operation, loading contingency command sequences to handle anticipated failure scenarios and accepting that any unanticipated scenario occurring during the maintenance window would have to wait for the antenna's return to service before any response could be attempted. The team's preparation for this window, working through every plausible failure mode and encoding responses in advance, was an exercise in the engineering equivalent of writing a will, anticipating your own absence and trying to arrange things so that what matters most continues in your absence. The Deep Space Network faces its own resource constraints as the number of missions it supports grows. Current and near-future missions to Mars, Jupiter, and the outer solar system compete for antenna time with Voyager 2. The Voyager spacecraft receive a certain number of tracking passes per week, each lasting several hours, during which science and engineering data are collected from the downlink, and during which the uplink antenna is pointed at the spacecraft for potential command transmission. The number of tracking passes allocated to any mission is a function of the mission's scientific priority, its data rate, and the competing demands of other missions using the same infrastructure. As the Voyager missions approach their end of life and their data return diminishes due to instrument shutdowns and declining transmitter power, the scientific justification for maintaining their current allocation of antenna time weakens relative to the demands of active planetary missions. There will come a point, sometime in the early 2030s, when the signal from Voyager 2 falls below the Deep Space Network's detection threshold. This point is determined by the combination of the spacecraft's declining transmitter power as the RTGs continue to degrade and the increasing distance that requires the signal to travel. The date of final signal loss cannot be predicted precisely because it depends on how quickly the RTGs degrade, how effectively the mission team manages the remaining power budget, whether any unexpected failures occur that redirect power away from the transmitter, and whether any improvements to ground receiving systems can extend the detection threshold. Mission engineers have estimated that at least one instrument on each Voyager spacecraft could remain operational into the early 2030s, and that engineering telemetry might continue to be detectable for some time beyond that. But these are estimates carrying significant uncertainty, not predictions, and the physics driving the outcome does not respond to wishes. The last signal and what follows it. Sometime in the early to mid-2030s, a tracking session at one of the Deep Space Network's facilities will find nothing where Voyager 2's signal should be. The event will not be immediately certain as final. Mission controllers will schedule follow-up sessions, apply every available processing technique to improve sensitivity, check equipment calibration, rule out local interference. They will do everything that can be done. And eventually, after enough sessions return the same result, they will conclude what they have known was coming. The signal is gone. The spacecraft itself will not have stopped transmitting at the moment of signal loss. The transmitter may continue to operate for some time afterward, pushing its steadily weakening signal outward through the expanding sphere of space surrounding Voyager 2's position. But the signal will have fallen below the minimum power threshold that even the Deep Space Network's most sensitive receivers can detect. The electromagnetic energy is still there, still propagating outward at the speed of light, still carrying whatever information the transmitter is sending. It simply cannot be distinguished from the natural background electromagnetic noise of the universe with any instrument that earthbound physics and engineering can construct. In that condition, Voyager 2 will continue. The spacecraft's momentum, accumulated through 47 years of travel and 4 planetary gravity assists, will carry it outward at approximately 15.4 kilometers per second relative to the Sun, roughly 34,000 miles per hour, without any thrust and without any significant deceleration. The interstellar medium is too sparse to slow it meaningfully on any human timescale. A spacecraft travelling at 15.4 kilometers per second through a medium containing approximately 1 particle per cubic meter encounters so little drag that the velocity change over 1 million years is negligible. Voyager 2 will travel at essentially its current speed for timescales that dwarf the entirety of human history. 300 years after the final signal, Voyager 2 will reach the inner boundary of the Oort cloud, the vast spherical shell of icy objects that represents the outermost gravitationally bound region of the solar system. The Oort cloud is thought to extend from roughly 1,000 to 100,000 astronomical units from the Sun, containing perhaps trillions of cometary nuclei, remnants of the solar system's formation preserved in the deep freeze of interstellar space for more than 4 billion years. Voyager 2 will enter this cloud as a dead machine, instruments silent, transmitter silent, attitude control systems exhausted of fuel, antenna pointing at nothing in particular. It will pass through an environment containing more scientifically interesting objects per unit volume than almost anywhere else in the solar system without detecting any of them, because it has no functioning instruments and has not had any for decades. The transit through the Oort cloud will take approximately 30,000 years. 30,000 years in which the spacecraft moves through a region no human-made probe has ever reached while functioning, surrounded by primordial icy bodies that preserve conditions from the solar system's earliest history, unable to send back a single observation. The spacecraft will emerge from the Oort cloud on the far side tens of thousands of years from now, having contributed nothing to human knowledge during the entire transit, despite being physically present in a scientifically valuable region. In approximately 40,000 years, Voyager 2 will make its closest approach to another stellar system, Ross 248, a red dwarf approximately 10 light-years from the Sun. The pass will occur at a distance of approximately 1.7 light-years. At this distance, even if Ross 248 has planets, and those planets harbour intelligence with technology equivalent to our own, detecting Voyager 2 would require sensitivity orders of magnitude beyond what any current human technology approaches. The probability of detection, honestly assessed, is so small as to be effectively zero. What continues beyond that is drift. Silent, purposeless, permanent drift through the galaxy, the trajectory slowly altered by gravitational encounters with passing stars and interstellar gas clouds over millions and billions of years, eventually merging with the gravitational dynamics of a galaxy that will itself be transformed by its collision and merger with the Andromeda Galaxy approximately 4.5 billion years from now. Voyager 2 will still be out there when the Milky Way and Andromeda are in the final stages of their merger, when the Sun has expanded into a red giant and consumed the inner planets, when Earth as a recognizable world no longer exists. The spacecraft will be a cold, dark object, its plutonium largely decayed, its golden record intact, its instruments long since silent, moving through a galaxy that has no knowledge of its existence. The final destination of Voyager 2 is therefore not a place at all. It is the condition of permanent, silent drift, the state of an object that was once connected to the civilization that built it, and has now been separated from that civilization permanently, moving forever through a universe that does not know it is there. The destination that most accounts emphasize, the one measured in billions of years and trillions of miles, is real, and it is also irrelevant. What matters is the window between now and silence, the years remaining in which Voyager 2's instruments are still operating, its transmitter is still sending, and its measurements are still contributing to human knowledge of the universe it passes through. That window is closing. It cannot be reopened. The magnetic field measurements and why they are the last window. After the cosmic ray subsystem shuts down in 2026, two instruments will remain on Voyager 2. The magnetometer and the plasma wave subsystem. These are not the most dramatic instruments the spacecraft has carried. They do not produce images. They do not directly sample the particles flowing through the medium around them in the way the plasma science experiment did. They measure fields and waves, quantities that require interpretation through theoretical models to yield physical meaning. But in the interstellar medium at Voyager 2's current distance, they are the most important instruments still operating, because they are measuring something that no other instrument anywhere can measure, and that determines physical properties of the solar system's galactic environment that matter on time scales stretching millions of years into both the past and the future. The magnetometer on Voyager 2 is a fluxgate magnetometer mounted on a long boom extending from the spacecraft bus, designed to detect the direction and magnitude of the ambient magnetic field, while minimizing interference from the spacecraft's own electrical systems. Magnetic fields in the interstellar medium are extraordinarily weak by everyday standards. The interstellar magnetic field in the local neighborhood of the Sun is estimated at approximately 1.8 to 3 microgauss, where 1 Gauss is the approximate field strength at Earth's surface. A microgauss is 1/millionth of that. Detecting fields at these levels requires an instrument sensitive enough to register changes smaller than 1/billionth of a Gauss, operating on a spacecraft that has its own electromagnetic environment generated by electrical currents in its systems. The long boom that puts physical distance between the magnetometer sensors and the spacecraft bus was essential to making the measurement possible, and it has been doing its job since 1977. What the magnetometer has been finding in the local interstellar medium since the heliopause crossing differs from what most pre-crossing models predicted. The models generally assumed the local interstellar magnetic field would be relatively uniform in direction and magnitude, reflecting the large-scale structure of the galactic magnetic field in the Orion arm of the Milky Way, where the solar system resides. The actual measurements show more complexity. The field direction in the interstellar medium just beyond the heliopause does not align cleanly with the expected large-scale galactic field direction. It shows variations that suggest turbulence or distortion from the heliosphere's interaction with its surroundings. Crucially, the field does not appear to have settled into a uniform undisturbed configuration, even now, years after the heliopause crossing. Fluctuations in field strength and direction continue to appear in the data, suggesting the spacecraft is still moving through a region influenced by the heliosphere's presence, a wake of disturbance that extends further into the interstellar medium than models anticipated. Whether and when the magnetometer data will show a transition to a truly undisturbed field depends on how far this disturbed region extends. That question is one of the central scientific problems the magnetometer is positioned to address if it survives long enough. The scientific value of continued magnetic field measurements extends beyond characterizing the local interstellar environment. The interstellar magnetic field directly affects how cosmic rays propagate through the medium. Charged particles moving through a magnetic field are deflected by the Lorentz force, which curves their paths. In a turbulent field with irregularities at many scales, cosmic rays undergo a random walk rather than travelling in straight lines. And the statistical properties of this random walk determine how long cosmic rays of any given energy take to travel from their sources to any given location. Understanding the magnetic field structure in the local interstellar medium constrains models of cosmic ray propagation, which in turn determine the predicted cosmic ray flux at the heliosphere boundary, which determines how effectively the heliosphere modulates the cosmic rays reaching Earth. This chain of dependencies means that every measurement the magnetometer makes contributes, indirectly but genuinely, to understanding the radiation environment of the inner solar system. It is not abstract physics. It connects to the biological history of Earth, to the variations in cosmic ray flux over geological time that influence mutation rates and possibly evolutionary events, and to the conditions that future human civilization in space will have to contend with. Measuring it directly, with an instrument physically present in the local interstellar medium, is something that has never been possible before Voyager, and will not be possible again for decades after Voyager goes silent. The plasma wave subsystem provides complementary information by detecting oscillations in the electric field of the plasma surrounding the spacecraft. These oscillations arise when the plasma is disturbed, either by shock waves propagating outward from the Sun, by turbulence in the interstellar flow, or by the natural thermal motions of the plasma particles. The frequency and amplitude of these oscillations encode information about the plasma's density and temperature. When the plasma wave subsystem detects a coherent oscillation at a specific frequency, the frequency corresponds to the electron plasma frequency, which depends on the square root of the electron density. From this relationship, the electron density can be calculated. This indirect density measurement is less precise than the direct measurement that the now defunct plasma science experiment provided, but it has one advantage: it requires less power and generates useful data even in conditions where the plasma flow direction is geometrically inconvenient for the direct sampling approach. The plasma wave subsystem has been the instrument that revealed the persistent, low-frequency hum in the interstellar plasma, the baseline oscillation of the local interstellar medium, which is one of the most haunting and most scientifically valuable findings of the post-heliopause mission phase. The persistent hum and what it means. In 2021, Stella Ocker at Cornell University, working with Shami Chatterjee and James Cordes, published an analysis of Voyager 2's plasma wave subsystem data that revealed something unexpected: a persistent, low-level oscillation in the interstellar plasma that had been present continuously since shortly after the heliopause crossing in 2018. The signal was faint, barely above the instrument's noise floor, and it had been present in the data from the beginning of the interstellar phase without being highlighted as a distinct discovery. When Ocker and her collaborators extracted it carefully from the noise and characterized it statistically, it turned out to be one of the most scientifically significant features in the entire post-heliopause dataset. The hum is a plasma wave oscillation at a frequency determined by the electron density of the surrounding medium. It is not a sound wave in the conventional sense. Human ears cannot detect it. It propagates through the charged plasma as an electromagnetic oscillation, a coherent movement of electrons in the medium that produces a detectable variation in the electric field at the spacecraft's antenna. From the frequency of this oscillation, Ocker's team could calculate the electron density of the local interstellar medium with higher precision and temporal resolution than any previous measurement. What the analysis revealed was that the electron density of the interstellar plasma, inferred from the hum frequency, was not uniform over time. It varied on timescales of months, changing in ways that correlated with pressure pulses propagating outward from the Sun. When a large coronal mass ejection or a series of solar flares produced a pressure wave in the solar wind, that wave travelled outward through the heliosphere, crossed the heliopause, and continued into the interstellar medium as a density compression. As the compression passed Voyager 2's location, the plasma wave subsystem detected a change in the hum frequency corresponding to the temporary increase in electron density. This was an entirely new kind of observation. For the first time, scientists could track the propagation of solar disturbances from their origin at the Sun, through the entire heliosphere, across the heliopause, and into the interstellar medium, all using data from a single spacecraft in two very different regimes. The timing and character of the density changes in the interstellar medium, compared with the solar events that produce them, provided direct measurements of how fast pressure waves travel through the outer heliosphere and heliopause transition region. These propagation speeds are quantities that models had estimated but never directly measured. The result was not merely confirmation of expected behavior at a refined precision. The propagation speeds measured from the correlation between solar events and Voyager 2's interstellar density changes were in some cases different from model predictions, indicating that the outer heliosphere and heliopause region have physical properties that the models had not accurately captured. The interaction between the solar wind and the interstellar medium at the heliopause, it turned out, was not a simple pressure boundary that transmitted waves cleanly at theoretically predicted speeds. It was a more complex dynamical interface that modified and reflected the pressure waves in ways that required revised physical understanding. The hum itself, the baseline oscillation independent of any specific solar event, also carried information. Its frequency implied an electron density of approximately 0.055 electrons per cubic centimetre at the times when no solar disturbance was present. This background density value, measured over multiple years and multiple quiet intervals between solar events, provides the most precise direct measurement available of the ambient electron density in the local interstellar medium near the solar system. It is a number with real physical significance. It constrains models of how the local interstellar cloud, the warm partially ionized structure within which the solar system is currently embedded, interacts with the heliosphere, and how the heliosphere's size and shielding properties depend on the properties of its immediate environment. Ocker's analysis was published while the plasma wave subsystem was still operating alongside the plasma science experiment and the low-energy charged particle instrument. The dataset that produced the discovery was accumulated over the first 3 years of the post-heliopause mission phase, when several instruments were still contributing complementary measurements. Going forward, with the plasma science experiment and the low-energy charged particle instrument both shut down, the plasma wave subsystem is carrying more of the scientific burden than it was designed for. It is doing more with less, as the entire mission has been doing for decades, and it is doing so on a power budget that continues to shrink. The hum will continue to be measured for as long as the plasma wave subsystem operates. Each new measurement adds to the temporal baseline of the observation, extending the record of interstellar electron density variations over time. Each new solar event that propagates into the interstellar medium and is detected by the subsystem adds another data point to the propagation speed dataset. The longer the instrument operates, the richer the scientific return. The power curve does not care about scientific return. It declines at 4 watts per year, regardless of what the plasma wave subsystem is detecting, and the day will come when there is not enough power to keep it running. The engineers who have spent their careers saying goodbye. The Voyager mission at the Jet Propulsion Laboratory is managed by a small team. not dozens of flight controllers spread across multiple shifts in a large operations centre, but a compact group of engineers and scientists who have, in many cases, spent the better part of their professional lives maintaining contact with 2 spacecraft that were launched before most of them were born. The human dimension of managing a dying mission across interstellar distances is rarely covered in the technical literature, but it shapes every decision the team makes and every compromise they accept. Suzanne Dodd has been the project manager for the Voyager interstellar mission since 2010. In interviews over the years, she has described the experience of managing the mission's decline as genuinely difficult, not just technically, but emotionally. The spacecraft are not abstract systems to the people who have worked with them for decades. They are familiar objects with known quirks, documented anomaly histories, and behaviours that experienced engineers have learned to anticipate. The 2023 antenna pointing anomaly that took 2 weeks to resolve was experienced not only as an engineering challenge, but as a threat to something the team cares about, in a way that is not entirely captured by professional language. The decisions about which instruments to shut down are made through a process that involves consultation with the broader scientific community, assessment of the remaining power margins, evaluation of each instrument's scientific return in the current mission environment, and ultimately a recommendation from the project team to NASA program management. These decisions are not arbitrary and they are not made lightly. When the plasma science experiment was shut down in October 2024, the team had extensive internal discussions about the trade-offs involved. The instrument's geometric limitations in the interstellar environment had reduced but not eliminated its scientific value. The power freed by shutting it down could extend the operational life of other instruments by months. The decision was scientifically justified. It was also a loss that the team felt. Ed Stone served as the Voyager project scientist from 1972 until 2022, a tenure of 50 years that spanned the entire active mission life. From launch through the heliopause crossings of both spacecraft and into the post-crossing interstellar phase. His retirement from the project science role in 2022 marked the end of an era within the mission. The transition from scientists who had been directly involved in designing and interpreting the original planetary science to a new generation working primarily in the context of the interstellar mission that the original designers had not specifically anticipated. Stone's public statements about the mission over the decades have consistently emphasized the unexpected nature of its longevity and the scientific value that persisted long past any reasonable expectation. In a 2022 interview, he described the experience of watching Voyager 2 cross the heliopause as one of the most profound scientific events of his career, and noted that the measurement would not have been possible if not for decisions made decades earlier to preserve the plasma science experiment when other instruments were being shut down. The team that manages the mission now operates with the knowledge that they are in the final chapter. They know the power budget. They know the instrument shutdown schedule. They know the rough timeline for final signal loss. This knowledge shapes how they allocate their attention, how they prioritize observations, and how they communicate with the broader scientific community about what the mission can still accomplish. There is an urgency in the current phase of operations that was not present when the spacecraft had decades of operations still ahead of them. Every tracking session matters. Every anomaly that requires investigation consumes time and resources that could be devoted to data analysis. The mission is in a mode of maximum extraction, trying to generate the most scientific return from the minimum remaining resources. The engineering culture at JPL surrounding the Voyager mission is one of quiet pride and genuine grief. Pride in the extraordinary longevity of 2 spacecraft that have vastly exceeded their design life and their original mission scope. Grief at the approaching end of a connection that has lasted longer than most of the careers of the people maintaining it. The engineers who work on Voyager 2 in 2026 are managing a spacecraft that launched when they were children or before they were born, that has travelled farther than anything humans have ever built, and that they will watch fall silent sometime in the next decade without any ability to prevent it. That experience is unique in the history of space exploration, and it deserves more acknowledgement than it typically receives in the technical descriptions of the mission's end-of-life planning. What Voyager 2 has changed about how we understand the solar system. Before Voyager 2, the outer solar system was a collection of points of light and rough physical parameters. After Voyager 2, it was a collection of worlds with specific, detailed, individually extraordinary characters that no prior observation had suggested. The transformation in human understanding produced by this single mission is difficult to fully appreciate, because the knowledge it generated has been incorporated so thoroughly into the scientific framework that it no longer feels like discovered information. It feels like background fact. It was not always background fact. It was once completely unknown. Jupiter, before Voyager 2, was a banded gas giant with a great red spot. After Voyager 2, it was a world of active volcanoes on Io, the most volcanically active body in the solar system, with eruption plumes reaching heights of 300 kilometers above the surface and constantly resurfacing a moon without a single impact crater, because the volcanic activity buries them faster than they form. It was Europa's cracked, icy surface, hinting at a subsurface ocean of liquid water that subsequent missions would confirm. It was the complex, intricate structure of Jupiter's ring system, far more elaborate than the simple, faint ring that earlier observations had hinted at. It was the specific character of the Jovian magnetosphere, among the most powerful in the solar system, trapping charged particles and accelerating them to energies that would be lethal to any unshielded spacecraft or human attempting to orbit close to the planet. Saturn before Voyager 2 was the planet with rings. After Voyager 2, it was a world with a ring system of staggering internal complexity. Thousands of individual ringlets, gaps that should not exist under simple gravitational dynamics, spoke-like features that rotated with the planet's magnetic field rather than following Keplerian orbital mechanics, and the intricate geometry of the Cassini division, which Voyager 2's measurements revealed to be maintained by a gravitational resonance with the moon Mimas, rather than a simple empty gap. It was Enceladus, whose anomalously bright surface suggested an active resurfacing process that later missions would identify as geysers of water ice erupting from subsurface reservoirs. It was Titan's thick nitrogen atmosphere, denser at the surface than Earth's own, hiding a surface that Voyager 2 could not penetrate, but that subsequent observations by the Cassini spacecraft and the Huygens probe revealed to be covered with liquid hydrocarbon seas. Uranus and Neptune before Voyager 2 were almost entirely unknown. Uranus was a featureless blue-green sphere with no resolved surface details and a known system of rings discovered from Earth-based stellar occultation observations in 1977. Neptune was a blue dot whose atmospheric composition was roughly estimated from spectroscopy, but whose detailed properties, ring system, moon population, and magnetic field were essentially unknown. Voyager 2's encounters with both planets in 1986 and 1989 respectively transformed them from mysteries into characterized worlds. The tilted, off-center magnetic fields of both planets, the geologically tortured surface of Uranus's moon Miranda, suggesting a catastrophic disruption and reassembly event, the active nitrogen geysers on Neptune's moon Triton, despite surface temperatures of -235 degrees Celsius. The great dark spot on Neptune, comparable in scale to Earth itself. All of this was entirely unknown before Voyager 2 and has been known fact ever since. The heliosphere itself was unknown in its full character before Voyager. The concept of the heliosphere, the solar wind bubble extending far beyond the planets, was theoretically understood, but its actual properties, including its size, its boundary characteristics, and the behavior of the solar wind at extreme distances, were inferred rather than measured. Voyager 2's data from the outer heliosphere, the termination shock crossing in 2007, where the solar wind abruptly slowed from supersonic to subsonic speeds, the heliosheath region between the termination shock and the heliopause, and finally the heliopause crossing itself, and the post-crossing interstellar measurements transformed the heliosphere from a theoretical construction into a measured physical object whose properties are now known with genuine precision. Each of these transformations in understanding is a permanent addition to human knowledge. The data Voyager 2 sent back cannot be unmeasured. The images of active volcanoes on Io exist in the archives and will remain there. The electron density of the local interstellar medium measured by the plasma wave subsystem exists in the scientific record and will be cited for decades. The knowledge that Voyager 2 generated is not at risk from the spacecraft's declining power. What is at risk is the generation of new knowledge, the extension of the measurement record beyond what has already been accumulated. The past is secure, the future is closing. The termination shock and heliosheath. The termination shock is the inner boundary of the heliosheath, the turbulent region between the decelerated solar wind and the heliopause. It is where the solar wind, travelling at several hundred kilometres per second outward from the Sun, abruptly slows down to subsonic speeds as it encounters the back pressure of the interstellar medium acting through the heliopause. Before Voyager, the termination shock's existence was predicted theoretically, but its distance from the Sun and its physical properties were unknown. Voyager 1 crossed it in December 2004 at approximately 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at approximately 84 astronomical units, a significantly shorter distance that immediately revealed something important. The heliosphere is not symmetric. The difference in termination shock distances between the two spacecraft crossing points, separated in the heliosphere's northern and southern hemispheres respectively, was larger than most models had predicted. The heliosphere's shape, it turned out, was compressed on the southern side relative to the northern side. This asymmetry was subsequently attributed to the pressure of the interstellar magnetic field, which is not oriented symmetrically relative to the solar system's motion through the local interstellar medium. The field exerts a pressure that varies with direction, pushing more strongly on the side where the field lines are oriented to create more magnetic pressure, and this asymmetric pushing produces an asymmetric heliosphere. Voyager 2's southern hemisphere crossing confirmed this asymmetry with a direct measurement that models could be calibrated against. The heliosheath itself, the region between the termination shock and the heliopause, proved to be far more turbulent and dynamic than the relatively smooth transition zone that simple theoretical models had envisioned. The solar wind in the heliosheath decelerated from its supersonic interplanetary speed, flowed in complex patterns that reflected the turbulent mixing and thermalization of the slowed plasma. Energetic particles of various origins, from the anomalous cosmic rays accelerated at the termination shock, from galactic cosmic rays penetrating inward, and from particles reflected and re-accelerated at the heliopause, filled the heliosheath with a radiation environment significantly different from either the supersonic solar wind region inside the termination shock or the interstellar medium outside the heliopause. Voyager 2 spent approximately 11 years crossing the heliosheath, from the termination shock crossing in 2007 to the heliopause crossing in 2018. During that transit, its instruments documented the properties of this previously unmeasured region with a continuity that no future mission is positioned to replicate. The heliosheath thickness, as Voyager 2 measured it, approximately 35 astronomical units in the southern direction of the spacecraft's trajectory, provided a direct calibration point for models of heliospheric structure. The variations in particle populations, magnetic field strength, and plasma properties across the heliosheath provided data on the physical processes occurring in a region where the solar wind's energy is being dissipated against the incoming pressure of the interstellar medium. Some of the findings from the heliosheath transit were genuinely puzzling. The magnetic field direction in the heliosheath showed a series of sectors, regions, where the field pointed alternately inward and outward relative to the Sun, extending much further into the outer heliosphere than simple wind models predicted. These sectors are the imprint of the solar magnetic field structure, which alternates polarity as the Sun rotates, creating a spiraling pattern called the Parker spiral. Finding this alternating sector structure persisting far into the heliosheath meant that the solar magnetic field retained more coherent structure at extreme distances than models had assumed, a finding that revised the understanding of how magnetic energy is transported and dissipated at the outer edge of the heliosphere. The full scientific return from Voyager 2's heliosheath transit is still being analysed. Papers continue to appear in the literature drawing on the heliosheath dataset, identifying correlations and structures that were not apparent in the initial data analysis. This is a characteristic of truly unique datasets. Their full value is not realised immediately, but continues to yield insights as new analytical techniques are applied and as the scientific questions that the data can address become clearer in the context of subsequent developments. The Voyager heliosheath data will almost certainly continue to generate scientific publications for decades after the mission's end, just as data from Voyager's planetary encounters continued to appear in the literature for years after the encounters themselves. The pale blue dot and the limit of human perspective. On February 14, 1990, at Carl Sagan's request, Voyager 1 turned its camera backward toward the inner solar system and photographed Earth from a distance of approximately 6 billion kilometers, roughly 40 astronomical units. The resulting image showed Earth as a fraction of a pixel, a pale blue dot suspended in a ray of sunlight scattered by the camera's optics, surrounded by the vast darkness of interplanetary space. Sagan's meditation on this image, delivered in a 1994 lecture and published in his book of the same year, became one of the most widely quoted passages in popular science. In it, he argued that the image should give us pause, should make us reconsider the cosmic insignificance of the conflicts and pretensions of human civilizations, and should reinforce our responsibility to one another and to the fragile planet we share. Voyager 2 was not in a position to take a comparable photograph in 1990. It had been directed on a different trajectory after the Neptune encounter, angled away from the ecliptic plane rather than remaining within it, which placed it in a different part of the sky than Voyager 1. But the principle of the pale blue dot image applies to Voyager 2's entire mission. From its current position, Earth is not merely small, it is invisible. The Sun, from more than 130 astronomical units, is a star among stars, distinguishable from its neighbours by a careful astronomer with a precise star chart, but not visually distinct from any other bright point in the sky. Earth, orbiting that star at 1 astronomical unit, is a planet orbiting a star that is a point of light at a distance where planets cannot be resolved. Earth does not exist as a distinguishable object from Voyager 2's current vantage point. This invisibility is the ground truth of the pale blue dot insight. When Sagan pointed to the image and said that our planet is a very small stage in a vast cosmic arena, he was describing a perspective that has now been extended to distances where the stage is not merely small, but completely lost in the backdrop. Voyager 2 has travelled far enough that the question of where Earth is from the spacecraft's position requires a precise ephemeris calculation, not a photograph. The planet that built and launched the spacecraft, and that has been maintaining contact with it for nearly 5 decades, is, from the spacecraft's current location, a theoretical construct resolvable only through orbital mechanics rather than a visible object in the sky. The pale blue dot image was taken while Voyager 1 still had functioning cameras. Voyager 2 does not have functioning cameras and has not had them for decades. The cameras were shut down after the Neptune encounter in 1989, not because they failed, but because the primary scientific imaging mission was complete and the power they consumed was needed for other purposes. This is the ordinary logic of mission management. Instruments are shut down when their scientific return no longer justifies their power consumption, and the cameras had done their work. But the consequence is that there will be no pale blue dot image from Voyager 2's current position or from any greater distance it will reach while still operating. There will be no visual record of Earth from the interstellar medium seen by a human-made instrument actually present in that environment. The pale blue dot as a cultural artifact exists because Sagan had the foresight to request the photograph before the cameras were shut down, and because the Voyager program was willing to spend the resources required to take it. It represents a deliberate choice to create a document of human perspective at a moment when that perspective was achievable and before the window closed. The equivalent moment for Voyager 2, in the context of its interstellar mission, is now. The measurements being made now, the data being accumulated about the local interstellar medium, are the interstellar phase equivalent of the pale blue dot, a record of human scientific presence at a location and in a context that will not be revisited within any predictable future. Whether those measurements receive the cultural attention they deserve is a different question, but their scientific and historical significance is not smaller than the significance of a photograph of Earth from 40 astronomical units. What no other mission has measured, and why none will for decades. The scientific uniqueness of Voyager 2's current mission phase is not merely a matter of being first, it is a matter of being only. There is no second active mission in the interstellar medium. There is no funded and approved mission that will reach the interstellar medium within the careers of most people currently in graduate school studying astrophysics or heliophysics. The gap between Voyager 2's end of mission and any future direct measurement of the interstellar medium is measured not in years, but in decades and possibly in the lifetimes of people currently alive. The interstellar probe concept developed at the Johns Hopkins Applied Physics Laboratory, led by Ralph McNutt and subsequently by Pontus Brandt, represents the most detailed planning effort for a dedicated interstellar precursor mission. The concept envisions a spacecraft launched on a solar gravity assist trajectory, flying close to the Sun to gain a large velocity boost from the concentrated solar gravitational field, then travelling outward at speeds significantly higher than Voyager's current velocity and reaching 1,000 astronomical units from the Sun within 50 years of launch. At 1,000 astronomical units, the spacecraft would be far deeper into the interstellar medium than any current spacecraft has reached, and it would carry modern instruments with capabilities vastly exceeding those of Voyager 2's 1970s technology. The interstellar probe concept received a positive evaluation in the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, which is the community-wide prioritization process that guides NASA's mission development investments. The Decadal Survey recommended that a dedicated interstellar probe mission be studied with the goal of initiating development during the 2030s. This is an encouraging endorsement, but it is not a funded mission. It is a recommendation for further study. The path from a Decadal Survey recommendation to a launch spacecraft involves funding approvals, competitive proposal processes, technology development, spacecraft design and fabrication, testing, and launch, a process that typically takes 15 to 20 years from initial funding authorization to launch. Even on an optimistic schedule, an interstellar probe mission would not launch before the mid-2040s and would not reach the heliopause for decades after that. In the intervening period between Voyager 2's end of mission and any successor's arrival in the interstellar medium, the direct measurement record will be frozen. Scientists studying the local interstellar medium will have the Voyager 1 and Voyager 2 datasets to work with. Two measurement trajectories, each sampling a different region of the heliospheric boundary, each providing a sequence of measurements from the heliopause outward for whatever distance the spacecraft travelled while their instruments were still operating. These are extraordinary datasets, but they represent only 2 points and 2 trajectories in a three-dimensional environment that varies with position, direction, and time. Questions about how the interstellar medium varies in different directions around the heliosphere, how it changes over the solar cycle, how it responds to major solar activity events at distances further than Voyager 2 will reach before going silent, will all remain in the domain of models and inferences rather than direct measurements. The science questions that motivate the interstellar probe concept are specific and urgent by the standards of the relevant research communities. How does the heliosphere's shape vary around its boundary? What is the nature of the interface between the heliosphere and the local interstellar cloud? How do the properties of the local interstellar medium change over distances of hundreds to thousands of astronomical units? What is the source of the anomalous cosmic rays? How does the interstellar magnetic field connect to the heliospheric magnetic field at the boundary? None of these questions will be fully answered by the Voyager data, and none can be answered without another direct measurement mission. Voyager 2's final years of data collection are therefore not merely the continuation of a historically important mission. They are the last data that will be added to a scientific record that must sustain the entire heliospheric and interstellar physics community for an indeterminate period, potentially decades, before it can be supplemented. This places unusual weight on maximizing the scientific return from every remaining year of Voyager 2's operation. The mission team at JPL is aware of this. The scientific community working with Voyager data is aware of this. The decisions about which instruments to preserve and for how long are made with consciousness of the fact that the resulting dataset will be the only direct interstellar medium data available for potentially the next generation of researchers. The Oort cloud that Voyager 2 will never see. The Oort cloud is the outermost region of the solar system, a vast spherical shell of icy objects extending from roughly 1,000 to 100,000 astronomical units from the Sun. It contains an estimated 1 trillion or more individual objects, each a remnant of the solar system's formation, preserved in the deep freeze of interstellar space for more than 4 billion years. No human-made probe has ever directly sampled the Oort cloud. No human-made probe has even reached its inner boundary. Voyager 2, travelling at 3.1 astronomical units per year, is approximately 143 astronomical units from the Sun and will not reach the inner Oort cloud for approximately 300 years. Its instruments will be silent before it travels 1% of the distance to the Oort cloud's inner edge. The Oort cloud occupies a special place in solar system science because it represents the boundary between the region shaped by the Sun's gravitational dominance and the region where galactic tidal forces and the gravitational perturbations of passing stars begin to become significant. Objects in the outer Oort cloud are held only weakly by the Sun's gravity, and interactions with passing stars, molecular clouds, or the galactic tide can perturb their orbits, sending some of them on long-period trajectories that bring them into the inner solar system as comets visible from Earth. The Oort cloud is the source of the long-period comets that occasionally grace Earth's sky, objects that have spent billions of years in the deep outer solar system and carry chemical signatures of the solar system's earliest period preserved in their frozen surfaces. Understanding the Oort cloud is understanding the solar system's deep history and its ongoing relationship with the galactic environment. The density and size distribution of Oort cloud objects, the fraction of them that have been ejected from the inner solar system versus captured from other stellar systems during the Sun's early history in its birth cluster, the chemical composition of their surfaces, and the dynamical processes by which the galactic tide and stellar perturbations shape their orbital distribution. All these questions connect to fundamental questions about how planetary systems form, evolve, and interact with their galactic neighbourhoods. Voyager 2 will pass through the Oort cloud's inner region at some point in the early 23rd century. It will spend tens of thousands of years crossing the full extent of the cloud, if the cloud has the structure that current models predict. and it will detect none of it. The magnetometer will be off. The plasma wave subsystem will be off. The cosmic ray subsystem will have been off since 2026. The cameras that might have photographed passing cometary nuclei were shut down in 1989. The spacecraft will move through an environment containing perhaps the most scientifically valuable objects accessible anywhere beyond the major planets. Objects that preserve 4-billion-year-old chemical records of the solar system's birth, and it will be as scientifically inert as a piece of space debris. The contrast between what the Oort cloud contains and what Voyager 2 will be capable of doing when it arrives there is one of the starkest illustrations of the mission's actual trajectory. The spacecraft that revolutionized understanding of the outer planets, that crossed the termination shock and the heliopause, that measured the interstellar plasma and the interstellar magnetic field, will drift through the most ancient and chemically pristine region of the solar system as a dark, inert object incapable of contributing a single observation to human knowledge. 300 years of silence before arrival, then 30,000 years of transit through scientifically extraordinary territory. All of it wasted by the simple physics of radioactive decay. The Oort cloud represents the final missed opportunity in Voyager 2's long sequence of achievements. The spacecraft could not carry enough power to survive for centuries. This was never a realistic design goal, but the fact remains that the most distant reaches of the solar system, the region where the Sun's gravity gives way to the galactic environment, the region that connects the solar system to the broader context of the Milky Way, will be passed through by humanity's most distant spacecraft without a single measurement being made. The culture of Voyager and what it means to let go. Voyager 2 has been travelling through space for longer than most human institutions maintain coherent identity. The Soviet Union that existed when it launched has been dissolved for more than 3 decades. The Cold War that shaped the political context of its launch is history. The technologies that seemed cutting edge in 1977, from the spacecraft's own computers to the mainframe systems at JPL that processed its data, have been superseded by many generations of successors. The world is comprehensively different from the world that built Voyager 2, and yet the spacecraft is still out there, still talking, still the most distant human-made object with functioning instruments anywhere in the universe. This longevity has created a cultural attachment to the mission that is unusual even by the standards of a field accustomed to long-lived projects. The Voyager mission has persisted through multiple NASA budget cycles, multiple changes in NASA administrator, multiple shifts in the agency's strategic priorities, and multiple generational transitions in the scientific community. It has persisted because it continues to produce unique scientific data that cannot be obtained any other way, and because the cost of maintaining it, compared to the cost of any new mission that could replace its scientific function, is extremely low. A small team, a fixed amount of deep space network tracking time, and the continuing operation of instruments that have already been paid for constitute the entire ongoing investment. The scientific return per dollar spent is, by any measure, extraordinary. The attachment is not only practical, there is genuine sentiment surrounding the Voyager mission within the space science community and within the broader culture that follows space exploration. The spacecraft represents something that resonates deeply, the human impulse to send something as far as possible, to reach beyond the known, to maintain a presence in a place no person can go. They carry golden records. They have travelled farther than anything we have built. They have been functioning for nearly 5 decades. These are not abstract facts. They evoke responses in people that go beyond scientific interest. Managing the end of a mission with this kind of cultural weight is a responsibility that the team at JPL takes seriously. They communicate about the shutdown decisions openly, explaining the technical rationale and acknowledging the scientific loss. They describe the mission's remaining capabilities accurately, without either minimizing the significance of each shutdown or dramatizing the process in ways that are not scientifically justified. The tone is one of careful, sober stewardship of something that matters, handled with the respect it deserves by people who understand both its technical reality and its broader significance. The act of letting go, when it comes, will not be a single moment. There will be no official decommissioning ceremony. There will be no controlled final transmission, no planned last message. The end will come gradually, as it has been coming gradually since the first instruments were shut down. A weakening signal, reduced data rates, eventually a noise floor that the spacecraft's transmissions can no longer rise above. The team will continue to track the spacecraft until the signal is genuinely gone, and they will continue to analyze the data after the signal stops. The archive will remain. The papers will continue to be written. The mission, in the scientific sense, will persist in the knowledge it generated long after the operational sense of the mission has ended. There is a quality to this kind of ending that is different from the dramatic conclusions that mark other chapters of space exploration history. The Apollo program ended with the departure of the last astronauts from the lunar surface. The Cassini spacecraft ended with a deliberate plunge into Saturn's atmosphere, its final transmission cut off by the planet itself. The Mars rovers have ended, or will end, when their systems finally fail under the conditions of an alien surface. These endings have a definiteness that Voyager 2's ending will not have. The spacecraft will simply become too quiet to hear, and the universe will reclaim the silence that the mission has been holding at bay for nearly 50 years. What remains after the signal fades? When the last signal from Voyager 2 is received on Earth and the mission officially closes, several things will persist that are worth accounting for precisely rather than abstractly. The data archive will persist. Every measurement the spacecraft has ever made, from the first Jupiter encounter images through the final plasma wave oscillation data from the local interstellar medium stored in NASA's planetary data system and accessible to any researcher with an internet connection. This archive is one of the most scientifically valuable collections of original data in the history of space exploration. It will be mined for insights for decades, probably for generations. The full scientific return from the Voyager mission will not be known for a long time after the mission ends. The knowledge that the mission generated will persist in textbook descriptions of the outer planets, in models of heliospheric structure, in measurements of the local interstellar medium density and magnetic field, in the confirmed crossing of the heliopause by 2 spacecraft in 2 different directions at 2 different times. This knowledge is now part of the background fabric of what humanity understands about the solar system and its galactic environment. It is not annotated as Voyager knowledge in most contexts. It has been absorbed into the general scientific understanding so thoroughly that it no longer carries its origin as a label. Future scientists who apply heliospheric models calibrated against Voyager data may not know they are using Voyager data any more than a GPS user knows they are using Einstein's general relativity. The knowledge has simply become part of what is known. The spacecraft itself will persist in interstellar space for timescales that make the mission's 5-decade lifetime infinitesimal by comparison. At 15.4 kilometers per second relative to the Sun, Voyager 2 will travel approximately 486 astronomical units per century, roughly 0.0077 light-years per century. In 1 million years, it will have travelled approximately 77 light-years. In 1 billion years, approximately 77,000 light-years, a significant fraction of the Milky Way's diameter. The galaxy itself will have changed substantially in that time. Stars will have formed and died, the galactic structure will have evolved, and the Milky Way will be in various stages of its collision and merger with the Andromeda Galaxy. Voyager 2 will be part of all of this, a silent witness to cosmic processes that dwarf the civilization that created it. The golden record will persist in its current physical condition, barring a direct collision with a solid object for geological timescales. The gold plating over the copper substrate prevents the oxidation and corrosion that would degrade an unprotected copper surface. The aluminum cover protects the playing surface from micrometeorite erosion, though at the extremely low densities of interstellar space, even unprotected surfaces degrade very slowly. The uranium-238 clock continues to tick at the pace of nuclear decay, accumulating in the form of its lead-206 daughter product in quantities that a sufficiently precise mass spectrometer could use to calculate the record's age from the moment it left Earth. The probability that any entity will ever find the record, recover it and read it is so small that discussing it in terms of probability is almost misleading. The correct statement is that the record will almost certainly never be found, and that this outcome does not diminish the significance of its creation or the value of what it represents about the civilization that made it. The golden record is not a functioning communication system. It is a monument to the impulse to communicate, preserved in the most durable physical form that 1977 technology could achieve, launched into the void on the most permanent trajectory that the laws of physics permit. The final destination of Voyager 2 is therefore not a place, but a condition, silence, drift, and the permanent separation of a spacecraft from the civilization that built it. The mission that began with a rocket launch from Cape Canaveral in August 1977 that transformed understanding of the outer planets, that crossed the boundary between the solar system and interstellar space, that provided humanity's first direct measurement of the interstellar plasma and the interstellar magnetic field, will end not with a bang or a ceremony, but with the gradual withdrawal of a signal into the noise. The engineers at JPL will know it is coming. They will try to extend the window as long as the physics allows, and eventually the physics will win, as it always does, and the silence will begin. Observation, decay, and silence. Voyager 2 is not simply travelling to somewhere, it is travelling away from everywhere that its existence as a functioning scientific instrument requires. The power curve that has been declining at 4 watts per year since 1977 will eventually intersect the minimum threshold needed to keep the transmitter above the noise floor of the deep space network. And at that point, the mission ends in the only sense that matters. The spacecraft continues. The mission does not. What makes this worse than most accounts acknowledge is the specificity of what is being lost. Not a spacecraft in the abstract, but the only active scientific instrument in the interstellar medium, measuring properties of the local interstellar environment that cannot be measured from Earth, and that no successor will measure for decades. Every instrument shut down reduces the resolution of humanity's portrait of the space between the stars. Every watt lost from the power budget closes another window on a region where every measurement is historically unprecedented. The data that will not be collected because the instruments shut down early, the plasma wave oscillations that will not be recorded, the magnetic field variations that will not be detected, do not exist anywhere. They are not stored in an archive awaiting future retrieval. They are simply not measured, and the universe does not hold them in reserve. The pale blue dot image exists because someone asked for it before the cameras were shut down. The interstellar plasma density dataset exists because someone preserved the plasma science experiment long enough to make the heliopause crossing measurement. The record of solar disturbances propagating into the interstellar medium exists because the plasma wave subsystem survived to detect them. Every piece of scientific knowledge that Voyager 2 has generated exists because a specific set of decisions made under specific resource constraints at specific moments over nearly 5 decades resulted in the relevant instrument being operational at the relevant time. The decisions still being made about which instruments to preserve and for how long are of exactly this character. They determine what will and will not exist in the scientific record of the local interstellar medium at the specific distance and trajectory that Voyager 2 occupies. The spacecraft will drift for billions of years after the signal fades. The golden record will carry its encoded portrait of humanity through the galaxy long after every monument, every building, every digital record of human civilization has been destroyed by time and stellar evolution. The plutonium in the radioisotope thermoelectric generators will continue to decay at the rate prescribed by nuclear physics, the heat it produces slowly dropping toward the ambient temperature of interstellar space, the difference between them approaching zero over timescales that dwarf human comprehension. And somewhere in the archives at the Jet Propulsion Laboratory, the last data packet from Voyager 2 will sit in a database, undistinguished from the billions of packets that preceded it except by being the last, carrying the final measurement that humanity's most distant scientific instrument was able to make before the power ran out and the silence began.